So now we have done the theory, we know what the X-rays are. We know that we need the instrument. This is the diffractometer, which is using X-rays, and we have to now record all the reflections coming from the crystal. And these crystals then appear as numbers from the instrument. And now we are really taking in their instrument data and start to look what is the structure, where does this diffraction come from. And now our target now is to use the data. We got it, somebody gave it to us, they made the measurements, and okay, here is the data. And they tell us, okay, it should be small chiral molecule. And this is now a walkthrough. I'm using a program set called Olex2, and there is the link for this, and you can get it, it's free of charge. All the programs are available, you can use them. Its academic use is free. You don't have to worry about this. And there are other programs inside this Olex2 that I'll show also, and we made it so that they will be available to you. We'll make a link. They're quite big, but you can do it easily and really easy to install. So you can then install these programs to your own computer and do the work based on this. Because you will also get the data. So you get exactly the same thing. So you can repeat the same thing what I'm doing here. You can do it at home with your own computer. And that's the essence in that sense. And then you can see actually what comes out. How does the real work, or how is the real work done with the programs? And that's the reason why I don't go into the mathematics on the theory part, because the computer programs are nowadays so sophisticated, we don't have to worry about. They know what to do. And it's our business just to follow and see that, okay, is this correct? Because one important point there is that the X-rays don't know the atoms. They only know the electron density. And this comes out from the programs. There are automatic programs there which analyze the data, and they guess. That will be the first guess. Okay, this could be the case. But now even that one appears in the new programs as an electron density, not a map, but appears like atomic balls. But they have you don't know, it's just a ball. And you will see later when I go through step by step what is the case. And this is really exact thing how it's done in real life. So really, you can go there and we will provide these things again. We'll figure out the system, how you can get it, and then you can do it as you like. You don't have to, but if you are interested or you use X-ray diffraction on your own work and you are willing to do the work yourself, there might be a service, a measurement that they provide you the data, but if you are given the data with this, you should be able to do it yourself. Because it's not enough that you just do the structure, but you have to be able to analyze also the structure. And this we will do tomorrow. Tomorrow is the analysis part, and then finally the last lecture is I will show you real examples over my career over the 30 years or so, different kind of supramolecular structures, what you can do with it. So this is, I would say, relatively simple work now. It's not very complex. And always in this course I'm using excellent data. So there is nothing, no disorder or everything of this kind of a thing, that everything is as it should be. Of course, because you have to start from the good examples. So this is our target. And this is a typical way of getting information. So either you do it yourself or then somebody have given you a sample. Normally there is at least a rough estimate about the chemical composition. So in here we have 13 carbons, 10 hydrogen atoms, 1 chlorine, 3 fluorines, 2 nitrogens and 4 O atoms. So the molecular weight is about 330, it's a small molecule. And then tomorrow, in the lecture 10, I will show you structures where the molecular weight is 13,000. So it's a size of a small protein. But anything is done in the same way. It doesn't matter if it's a small molecule or a big molecule, the same thing applies. And then this is the cartoon of this. And now we already mentioned, okay, it's a chiral, but sometimes we don't know. We don't know, do we have an optically pure molecule, crystal, or do we have racemate? You remember racemate can crystallize also, and the pure enantiomers can crystallize. So in this case, we don't know yet if this is, we know that it's chiral, but we don't know if it's a pure enantiomer. And now it's a question, if it's a pure enantiomer, is it R or S or left-handed or right-handed? After that, we will know. So as I told you, X-ray diffraction is the only method which can reliably tell you what it is. Is it this one or that? That's the beauty of this. So that's the idea. So we have a benzene ring here, chlorine is attached here. We have here a 5-membered ring with 4 different atoms. So carbons and O and nitrogen. And there's a nitro group here, a methyl group, and there's CH2 in here. And this is our target carbon. You can see from this carbon, sp3 carbon, there are 4 different substituents. So this is the chiral carbon. So we have here R or S. And now our idea is now to look into. We have the data, we got the data, and the data seems fine, so we start the business. We start the engine. So it looks like this. So the Olex icon, when you install it, looks like this. So that's the idea. When it's there, we can click it and we can start the engine. So the point, it opens, and the opening window, it looks like this. So we work this thing through these screenshots of the program. So there appears a text which happens at which time. So it's very easy for you to follow the handout, because you just follow exactly what is here in the handout with your own program, then you can easily get it. So the idea is that it looks like this. When you open it first time, there might be a structure coming up, and if you look very carefully, you can see this is sucrose. It's a sugar molecule. Because there is some demo structures inside the program, and it automatically, if you haven't done anything, opens one of them, and it's typically sucrose. So that's the idea. Don't worry about this. That might look different, as Olex remembers the old work. And now it's sucrose. So that's the idea. And this is our graphics window, and there is some information in here. So now, what we do, we go in the upper left part here, and then say, File Open. So we click this File Open, and so when we click the file Open, and click Open, a menu appears. So this is the walkthrough. So I indicated each individual point what you have to click. Because of course you are not experts of using this program by itself, but now when you follow the walkthrough, then you can see what happens. Okay. It opens up a folder, and I normally always do it so that I indicate each structure has its own folder, because this program writes a lot of files. Some are needed, some are not, some are less important than the others, but they all go into one place. So that is very nice. So always give it a name. Now here the name of this folder as a demonstration 25. And there are 2 files. And now these 2 files comes from the instrument. And now you can see there is an ins file. It's very easy to understand. It's instruction file. And this instruction file has a certain format what the program on the diffractometer has already written. So it's ready to go. So it's our input file. It doesn't contain any information about the structure. It contains information about the unit cell and all the other things what the instrument can find. But it doesn't know, of course, the structure. And then the HKL here is the data file. And now, remember, what is the HKL? HKL is the lattice plane, and HKL is the Miller index, name for each plane. So this contains information on each of these planes. And there can be thousands of these. It's just a number. And now, the idea in here is that we now go in here, select the demo and click open. And now, it doesn't open like this, but I show you what are how do they files look like. So this is now the demo ins. So the point is, this is directly written by the diffractometer program, but the idea is there. It tells a cell, here, it's a parameter. This is our unit cell. So wavelength, A, B, C, alpha, beta, gamma. So you can see already, okay, it's orthorhombic system. Now, these are the errors. So this scans how many molecules we have there in the unit cell. It's 4. It's an orthorhombic system. It already, the diffractometer already guesses this. And then these are the errors. So this is the standard deviation of this. And now, these don't have a standard deviation because it's fixed. It's an orthorhombic system. And now, there's the information. Lattice is lattice 5, lattice -1, primitive non-centrosymmetric. So the program already went through the data, and it says that, okay, now it seems to be the data speaks in favor that there is no mirror image. And that is the non-centrosymmetric, so it's there. And now the symmetry operations, what are here, these are coming from the symmetry operations inside the unit cell. It thinks that it is. So it analyzes the data and sees, okay, it seems to be that these kind of symmetries are there based on the diffraction. And then this scattering factor, these are information about atom types, which kind of atom types you have in the structure. These we have already given when we are doing this, because the program has to have an idea what are the atom types we have. Because each of the atom type will diffract differently. The heavier atom, the more electrons there are, the stronger it diffracts. So we need to know them. We don't have to know them exactly, but if it's a big mistake here, it might cause some problems with the mathematics. And this is the actual how many atoms of these we have in the whole unit cell. So we in the unit cell have 52. Remember, it was C13. So 4 times C13 is 52. That's nothing more. So that is an information that comes from the instrument directly. And this is just an information about the format for this file. And now, this is now the HKL file. And this is how it looks. So look and see. 002, 002. 002 has been measured 2 times. And you can see the value is the same. And now, it's called the observed intensity. This is just a number. But this number now contains a tiny fraction of information of all atoms in the structure, but a very tiny one. So we have to collect all. Now you can see that it's a standard deviation, but now 003 is virtually 0. This is now 0. It means, okay, look, 003, where the L is odd, seems to be very small or 0. Look, 6, 0, 0, 3, minus. It seems that this 0, L equals an odd, is missing completely. And this is the information what the program has seen, and based on that information, so it considers that the symmetry operations inside that unit cell are those. So the data contains information. Earlier we have to do this by hand, and we have to go through each of them and see ourselves. And you can see now that 4 is a big number, 6 is a big number, 8 is a big number, 10, 12, and so on. But you can see there's variations. What this means that now, if you look for this number, 0012, there is a lot of information coming. So the intensity is high. That means that there has to be a lot of electrons on that plane. And in here, that's much less. There's virtually nothing, but still there. So that is the idea that these 2 files coming from the diffractometer are all we need. And there are, I can't remember, but we will soon see, I think some like a couple of thousand lines or whatever. So remember I showed you the CT scan of a brain, about 30 images. So you can consider each image is like this. So it's measured twice, but anyway. So the idea in there is collecting, putting them all together will give us the structure. And now that's the idea. Not the chiral carbon, that's the idea. So we have to figure it out. Is it enantiomerically pure or racemic? Now we start the engines. So now we click work, here in the upper menu, and now it opens in this way. It doesn't know anything yet, but you can see the idea now. When we click open, it reads the inst file, and now you can see it wrote our supposed chemical information in here. And now it reads the demo file and lists details in the upper side of the work menu here. That's the unit cell, that is the A, B, and C, that's the parameters and so on. These come from the old one, they don't relate to the structure at all. And then calculate Z. Z is the number of molecules in the unit cell, and the total unit cell. And that's the idea. So we don't see anything else yet, okay? Now it reads in, now the data has been read in. Now we go in here, click the solve button. It opens, we activate the solve button here, and it gives us a new menu. So you can see this part changed now. And in here we have, so we have two phases. We have to solve the program, so there is the program what is guessing the phase. Remember the phase problem we had, so that if you don't know the phase, we can't solve the structure because it's needed. But the point in there is that there has to be some way to estimate the phase, and there's a program for this. And this is the solving program. The programs are here. There are several options. So what we have to do is to select a proper program here. Now, the solve menu is now active. That's the yellow arrow here. And it shows the structure solution program, and data file name, and the chemical composition here. So now it says, it reads the demo HTML file, it knows that it's there, all the data is there. And now the chemical composition is here. So in principle, we can change this if we like, but this is okay for us. Yeah. We think that is correct, let's see what happens. So all these can be changed if needed, so we can have to do this. Okay, now, then we have to, because remember the computer program in the diffractometer already was looking through the data and guessing or looking, okay, is the symmetry operations in this unit cell, can it find, or some kind of thing, meaning that can it find the space group for this? The space group are the symmetry operations inside the unit cell, but we have to check this by ourselves. And there is a very nice button here, space group, suggest space group. So we click this, and it gives a listing of possible space group here or down here. So when you click this, it will list here these things. And you can see here it says P212121, which was, by the way, the same what the diffractometer program was doing. It was doing a very superficial check, but this reads the whole data. So we have to believe this. And now in this phase here, that small note, you can see that there is a name for the space group. So now the program knows this, and it will use the symmetry operations, what was mentioned, for this space group with this unit cell. And if these both are correct, the mathematics should work. So now, let's see what happens. So we now go here in the program menu, and you will have it later on. We use a program called Olex2. So that is a different set of programs, and by default, by teaching purposes, we are using an old version of a program which doesn't give everything at once. So it gives us a presentation of the electron density map. And this is the idea. So select this program, menu here, and then click solve. So then when this is there, we will click solve here, and it runs the program. So it starts there, the computer is now running the structure solution program called Olex2. There are many possibilities, I think 5 or 6 known of this kind of programs, but these Olex programs are very good, so we use this. So what happens then? Now, it did the program, it's nearly as fast as this. It happens in a second or so, and you get this kind of a strange looking blobs hanging in the space on this graphics window, and one is already green. So what happens? Olex program produces what we call the structure solution. This is not the structure, this is a structure solution, this is a guess. The program made a guess for the phases, and based on these phases it puts up something, and now it's our idea to look, does it look reasonable? Was the guess for the faces mathematically close, so close that we can see a reasonable chemical structure? And now this is reasonable chemical structure means electron density. And now the electron density already here is presented as balls, brown balls. So the idea is now visible. Some balls have color. The remaining brown ones are assigned electron density peaks. So we don't know what is the atom. We know that there's an atom. It seems to be that in this position, the brown balls, each of them represent an atom. But the point is there might be more of these peaks than there are real structures because we don't know what it is. So it's our business to start doing. So these are called Q peaks. We call them Q peaks. Q is unknown. And now the idea is that, okay, now we rotate the right mouse and drag. So you will show that in there. We rotate because it looks very bad. You can't see, it's just a blob. So we have to move it around. It's three-dimensional image. We can rotate and we will see something. So I will just show you before we go in there, how does it look? Because now, in this phase, when we do this is based on another file, which is called the res file, the results file. So the structure solution writes as a results file, into which it writes the coordinates of these things. And now when we look, it looks like this. That first part looks the same as in the ins file, but after that you will see a list of coordinates. And now there is one which says chlorine, and there are the coordinates, and then Q1 and so on and so on. Why is this? Because now it sees that the peak height, the mountain, was much bigger than the others, and it knows that there's chlorine. So the program automatically assigns that heaviest peak as chloride. All the others are unknown. So you can see it writes a new file, a results file, here a demo res. It contains electron density map with their here is the electron densities as a number. They are not related to any real numbers, but they are relative numbers. So that gives you, okay, you can see, if you look now carefully, start from 184, we go up there, it slowly goes down until 100 and then drops. So now if we start counting these things, it looks that there is exactly the same number of these heavier peaks that we have atoms in our structure. So it's promising. So that is the idea. Now, it has a maximum, is assigned, but now automatically write additional instructions here. We don't have to worry about this. Now we are back in here. Now I rotated that a bit. It looks different. It's the same blob. But now we look at on the different side, and now we can see that here we have a chlorine atom, which is already assigned, and then seems to be a, now, if you look carefully, we know from the beginning that chlorine atom should be bonded to a benzene ring. So we should see a hexagonal blobs, hexagonal brown balls there. And that's the actual idea. Rotating a model known can draw that there should be a benzene ring into which the chlorine atom is attached. We can now edit the model. So we can here, we have possibilities now in here. You can see labels, carbon, hydrogen. We can use these and then start assigning the atoms or the brown balls to an atom. So what we do, we click here carbon now, and lower left of the working menu activate the naming tool, and after clicking one by one, we start clicking 1, 2, 3, 4, 5, 6. And once we have done it, we have a benzene ring. And now you notice what happened. When I go backwards, look, there is no bond, because it doesn't know what atom this is. But immediately when we assign that atom there as a carbon, it knows that, okay, the bond distance here is suitable for a carbon-chlorine bond, and it draws the bond. So now we have chlorine atom attached to a benzene ring. That's fine. Okay. Now what we do, the model looks like this. And now what we have to do, so we have a guess for the phases that they're good enough that we can see the benzene ring. But now the benzene ring, this is a guess. We have to make it more accurate. So what we now do, we take this part in here and we move it slightly and compare that with our data. This is called refinement. So we will have an accurate position, more accurate, because now it's there. You can see, and then look carefully, they are all balls with the same size. The diameter of the ball has an importance. So we activate this menu here now, and now, okay, in here we must escape that we can get out from this thing, and we are now in there, and we go to the activation menu, refinement menu, and we click now. Check the change refinement program is Olex L, because this changes. So each of these menu have different set of programs, and now in here, in this refine menu, which is now activated, we will select Olex L. That's a refinement program, and now we change now the cycles here, how many times it will change this. It's 4 times, and it will look for 20 additional peaks. So these we call the peaks. Can it find out a correct atom? So we do this. So now click the weight. There is a weight button here. This is a mathematical add-on. What we have to do is a correction factor which always goes with it. So we click this and then click the ray refine button here. Now something interesting happens. So look, there is again the blob of these brown balls, and now you can see that they changed the size of the balls. And now what is happening is it's estimating the thermal movement of the atoms, because all the atoms are vibrating, so it estimates their thermal movement of these atoms as a sphere. You can see there are different size, don't worry about it. But now, the idea is that now when we have done it first time, now we have a real comparison with our model, which is this, and the data. So we get so-called R value. So this is an information how well our model fits with the data. And this is what we are doing. So this is feels interesting in that sense when we have a data contains all the information, and then we have more model. And now we have a partial model, so we don't see everything is here, but in this model we have only maybe 3 out of 5. So something is missing, and this is indicated by this number. So now around half of the structure is correct. So something is missing. As we know, there should be more atoms there when we have to locate all the atoms. So that's the idea. And notice the atoms of the model have changed now. And this we call an isotropic thermal motion. And the idea is that it's like a ball with its estimation the first time. It will be more accurate in the later. Okay, let's go on forward. And that's the idea of what we have in there. And now what we do, we change here, now, cycles to 10. So it will do more. So it will do more of these things, that it would stay, that we would have there is no movement anymore. Because what we do in here, we just slightly move the atoms that it finds the correct position. It always compares that with the data. So now let's rotate this again and look if there are atoms attached to the benzene ring, and we name them as carbon atoms. And this is the idea. We found that there are 3 brown balls in there, and we just click them as carbon, and we have them now here. Now we go back to the refinement here, and then see what we have. So now, this number went down a bit, and we have now located that this looks fine, okay? And now if you look for the ChemDraw drawing, you know that there is a carbon, and into this carbon there are 3 fluorines atoms attached. So when we look carefully, we see that there are 3 brown balls in here, and I already activated them in here and asked the program now to change them to fluoride. So our chemical knowledge tells that there should be a CF group in here attached to it. So here are the suitable peaks. I already activated them, and now I change them by this knob here, change them to fluoride. Okay, now we have that. We now go back again to this refine, and let's see what happens. Look, this number is going down all the time. So this number tells us that our model, what we are looking now, is now more accurate. It goes and fits better to the data. That's the idea. Now we can see, and also you can notice that the balls change slightly. They become more of a unique shape and size, but that's a movement. Okay? We have this here, and then the chlorides are there, additional brown beaks in there. Okay, now let's do a next step. Now the R value is this one. We also can use it as a fraction. And we can locate more of the missing atoms. So we rotate the model and see if we can locate more atoms. Well, we do this. And now, what we can do in here, there is a nice knob in here. That now, because the point is that the program doesn't know if the electron density is here or if the electron density is here. So it just wants to have it, but it doesn't know if they are close by. So this collect knob is really nice because it will collect, it will look if some of these brown balls, the electron densities, are close to each other, and it moves them there automatically. So we click it there, and now it turns out to be that it seems to be really that there is a 5-membered ring in here. And now our chemical knowledge tells that we should have a CH2 group and a 5-membered ring attached. So look. Seems to be that that could be the CH2, and that could be the 5-membered ring. Other peaks are also there, don't worry about it yet, but that's the idea. Well, let's see what happens. We start assigning them. Now select these peaks, and we put them all as carbon atoms. In principle, they should not be carbon atoms on the 5-membered ring, but we just name them as carbon atoms. We know that all in here are not carbon atoms, but let's fix them later. And then do the refine, click here again, and now we see, okay, now look. Now it's 27 anymore. So it's going down. So our model is getting more and more accurate. So now we see that there are 3 peaks close to the 5-membered ring. It would be the nitrogen O atom, the nitro group. So here, this thing. So now what we do, we rename them. So this would be nitrogen and O atom. And O atom, we rename it using this one, and then click this refine. Now we have a nitro group. And look, this dropped to 17. So the more atoms, correct atoms we find, the more accurate our model will be. That number will go down. So what we aim to do, to have this number as small as possible. And the Olex is very nice in that it uses colors. So when you have a green, it's okay. Orange is somewhere there, but the red means this kind of okay. Be careful, not ready yet. And the point is now, the observed drastic drop in there because only one atom is missing. So we have everything else except one atom is missing. We are now only looking for the amount of atoms. And the point is, this is the CH3 group attached to the 5-membered ring, and you can see it here. So now we rename this as carbon and repeat the same refinement. Now we have it, and now observe, look. The R value went to 13 and changed color. So we are now going out from the red to the orange color or yellow. And now we have all non-hydrogen atoms. We can see that from our structure, where the chemist gave us. Okay, yes, we have all the atoms. Seems to be that there's no other atoms. But now, some of them are incorrect. So how do we know that they're incorrect? You can see the ball size here. The ball size here indicates thermal movement. And now the thermal movement is associated with the atom type. Because each of the atoms have a different amount of electrons, and then they diffract differently. So if we have an incorrect atom type, you can see this in the diameter of the ball. So clearly now, the idea is that the thermal movement of the carbon atom in the chiral center is there. The item is now, sorry, you can't see it now, discuss about this, because we know that this carbon, which is hidden, I will show it in the program, there is an atom where we assigned as carbon, and that's really an O atom. So we have to change it. So we do this. So that one here in the back. So we go correct the atom type. This one here is not the carbon, it should be our O atom. We do this, and now refine. The value changes with now the atom type is correct, refine. The point, R value went down. So when we have a correct atom types in the correct positions, our model, so this is what we see here, fit better with the data. This is actually what we are doing. Now we have a correct atom type here, it's there. So observe our value is now, we have all the non-hydrogen and some are still of incorrect type. So from the chem draw, we know that the 5-membered ring atoms opposite to the nitro should be O and nitrogen. And now they are carbons. And now if I have to make a guess, the actual idea is that because if we put here, instead of O atom, we put a carbon, it will have too much electrons for a carbon and it moves less. So this diameter of this ball is smaller. But we know that from the chem draw, so we don't have to guess. To the point we know that this has to be the O atom. So we rename it, we just click here and name it as a carbon, or sorry, an O atom, and again repeat the same thing. Now the atom type is correct. And now we refine. We click here, refine. Again, there are values going down. And now you can see that we have it there. Now the observed value is we have not all the atoms still one incorrect type. From the chem draw we know that this is the idea and rename now this as a nitrogen atom and repeat. And now it still goes down. Now all the atoms are now correct. And the point now, we can do a trick. We will go here and reduce the number to 5 and see what happens, and then refine it again. Now you can see, when the refinement, you can see 5 Q peaks around the chlorine and fluorine atoms here. Look. Why is this? The idea is that because we have now, until now, the program is using so-called isotropic thermal movement. It means that it's the same movement in all directions. But this is not real. So in the real life, the atoms are moving anisotropically, meaning that the thermal movement in this direction is different than this direction. So we have to change this here inside, because this is what we call the residual electron density here. This indicates that this atom is actually moving. And you can show that as the brown ball close to it. So what we have to do is we have to go here, there's a nice knob in here, use anisotropic thermal parameters. So we click this, and now we refine as long as the weight, which is here now, it's green, but it will turn orange, but we will refine it as long as it's green. The green color is here. We can see a lot of green now already. So we do this, and now, with non-O, look what happens. 11.4, we change the atom types that they now are estimated. The thermal movement is taken into account, the real thermal movement. There's a drastic change. It drops to 4.8. And now it's green. And you can see how it appears. You can see ellipsoids in here now. And the idea is we go to the R value of 4.7, 4.8, and when the peaks are 5, we can see only 5 Q peaks, which should be hydrogen atoms. So our data is so good that we start seeing the ghost of a hydrogen. Hydrogen has only 1 electron, so it's not very good diffracting, but the idea we can see, okay, yes, there are, this could be the CH2 hydrogens. So what let's do is, so we'll change the peaks to 10, that's the number of the atoms, hydrogen atom structure, and then refine. Again, go and refine and click. And now, look what we see. The R value didn't change, but we see 10 Q peaks, which look very suitable as hydrogen atoms. We don't know the hydrogen atoms because we don't have to, because there is a very nice knob here, add hydrogen. So the program can calculate the hydrogen in a correct position. So now we click this one, so calculate then by clicking add hydrogen button in the lower corner, and now we have. And the hydrogens appear as small white balls here. And now with all the other non-hydrogen our calculated R value is now 3.6. So we started from 50 and we go to 3.6. So this means an error of 100. So this is 100 minus this number correct. So the idea that it's now 96% correct. And it's very difficult to get lower because there is always some faults in the data. So this is our R value, which is a very good value. And now the remaining peaks here are the background. We don't have to worry about it. We have all the atoms. So we now do reduce the peaks to 10 and refine, so that this goes like that. Now all is done. So this is our structure now. And you can see there's even hydrogen in all that. They are all calculated in there. And now what we have to do, you can see that always been a red box here on this side. And this means that we have to ask the program to write one very important file. This is our coordination file called CIF file. And then we change this to Acta in here and refine everything to the completeness. And now, you can see now Acta is green, all these are green, these are all green, and then this is also green. So everything is done. We have now done the structure, everything is there. So the final structure has this structure solved and refined to completeness. This is now what we managed to do. This is the walkthrough of this thing. And now the question is, okay, what is this? But I will show you a thing. I will show that also in there, because we have some time to do this. But now there is a more sophisticated program. And what happened? Because this old program was giving you the electron density, and you have to assign it yourself. But what happens with this? So you just simply go into this program here, and then change the S to T, and then click solve. Home. This is what it gives in one shot. So the Olex2 solves the structure, assigns all the electron densities. When we have a good quality crystal like in here, you can assign nearly all atoms correctly. As the carbon and nitrogen atoms have only one electron difference, they're difficult. So now that we notice that in the 5-membered ring here, the nitrogen appears as carbon. Everything else, and now here, this nitrogen appears as carbon and this O appears as nitrogen. What we have to do is just to change this. And this is what we do. We now rename these correctly, make them anisotropic from there, and add hydrogens as we did it in the previous case and refine. Now we have the same thing. And this is the whole thing. I will demonstrate that with the Olex2 now that it doesn't take too much time. So we are roughly on time. It takes about, I would say, 30 seconds, something like this. So all these things. So this is now the idea of refine everything. Everything's fine. You can see everything is green. And now you can see here a number. And this number appears only when we have a chiral structure with a pure enantiomer. And now we know that this molecule is enantiomerically pure and it's of correct handedness. And this is really important. There are values in here, and then this number is in green, then we know that we have a correct handedness. And it should be 0. If it's 1, then it's incorrect. And that's the idea. This is what the outcome is. So what we are doing here, actually, what we are making a model, and from this model we calculate the intensities. So the intensities are actually changed, so-called structure factors. I didn't show the mathematics for this, but don't worry, the computer is doing that. So now our model we can use to calculate the numbers, the structure factors, and which are also from the data. And then this comparison is the R value. So the closer our calculated, the calculated is our model, and then the observed is measured, are similar, the smaller is the R value. You can see they're very close. Look, tiny difference there, but in general, all these fit about 96%. And this is very good value. So then we are happy, everything is there, and that's the idea. This is just the standard deviation of these values. But that's what we do. We create from the electron density map, we create a model for our molecule and then compare these two things. And this is actually what we are doing. But now I will show you quickly the structure solution in real life. So here is the program. The icon looks slightly different than what is in the Mac because or in the Windows because this is the Mac version, but the program is the same. So it takes some time. It's rather slow to start. Hopefully it starts nicely. Let's see, it's there. It should be coming. Yes, it's there now. So we have it here. And now, this is now the thing. So you see how it is. What we do now, and don't worry about this. The Mac device is different, but here we have here the open file. And now here we have it remembers because I was checking this. There we have the two files. So there's the data file and then the index file, which is the same as you saw before. So what I will do, I will go in here and say open. And now it reads in the data. The data is there, and now you can see there is no information yet because we haven't done anything. So I will go now to the work, and now in the work here I will click. I'm sorry, no, it went incorrect. Sorry, I was too fast because my idea was to show you this now. So I was clicking the Texas space group. So in there it lists here now the space group, which is the symmetry operations. Okay, then it was too fast. I will do it again. Now you can see that the program is L14 here. So I will ask it to solve the structure again. So I will say, are you sure that you want to solve this again? I won't, because I want to do it again for you. Now you can see what happens. So this is the speed. And now, this is now the thing, what you can do. What you're doing here, you're looking for your structure. You can see now there's a benzene ring here, where the chloride is already. Now it already assigns the fluoride atoms here. This is the chiral carbon. There is the O atom, CH2, and then the 5-membered ring. But you can see now there are mistakes. So this cannot be true. So this one has to be O atom. So I'll change that to O atom. Or this is not correct. This has to be nitrogen atom. So I'll do it like this. And now we know also that this one here is not carbon. So it's nitrogen. So I will assign that to nitrogen. So now, we have all the atoms. This is how it works. And now what we go here in this menu. I will activate it. Now we refine. And now you can see that I haven't clicked the weight yet, but I will just refine it. So it's 4 cycles. So let's see what happens. Now, we got already 11% because it has all the atoms. We like a chant to the station where we have all the atoms right there. And now you can see the balls are spherical because we have the isotropic thermal movement in there. So this is, you can see the weight is now red because I haven't clicked it. So I click it and we do this refinement. Now you can see that it gives, it's orange yet, but never mind, something is missing. So the weight has to be there because in the mathematical it will balance between the calculated and observed values. So we always have to do this, but that's easy to do. It's just a follow. And you can see here a red tag here, which is how much our model is moving from the data, and we have to get this red one to green. So I will redo this. Now it went to green. So now we have all the atoms, but we have the isotropic thermal movement, which is the ball. So we have to change that to anisotropic, so that we will take into account. And that was this knob in here. So I will click this, it did it, and now we can see what happened. So the R value dropped to 7, and now the shape of the atoms changed to ellipsoid. And now you can see what happens. It's already assigned because I have here 11 peaks. So you can see now that, yes, there's one addition you can see here. This is clearly a ghost. It's not real because there can't be any hydrogen attached to this carbon or movement. But you can see here, this is nice. We can see a ghost. Obviously they are hydrogen atoms. And I can even do it so that I can activate this atom now and then say add hydrogen. So it will now add hydrogen on the activated thing, and then I will say refine. And you can see disappear. And this one here, which appears in this, is a ghost. So it's a background, it's nothing. Now, okay, I would be happy to have all the hydrogens replaced in there. I click add hydrogens, and then I will refine. Now we're there, look. And as long as this goes green, and this will green, we are happy, so we repeat it. Repeat it, we are there. Look now, all the numbers, except this one is green. We have all the atoms, and these things here are backgrounds. You can see that there cannot be anything here between these two atoms, but it's a background. This is a typical thing of us having these peaks. And these peaks, we can look the height of these peaks. I will look for example, this one. I will place this one here now. It gives a number, and it says this is Q4, and the height of this peak is 0.13, and hydrogen is 1. So we know that this cannot be anything because it's much less than 1. So we can in this way, but this is normally how we do the work, but we have a model. So we try to solve them based on the model. Okay, we know that this is the structure, this should be the case. Like in this case, we have the 2chem drawing in here. So I will reduce these peaks. So we will leave only 1. And now this is the highest peak in the background. And you can see that it's between these two things. So we know that there is nothing. So we have all the atoms we have located. And now it's chiral molecule, so the point in there is that this number here indicates that we have the correct enantiomer, and it's acceptable. But now the one thing is here that this is red, and then what we have to do is to change the octa and then refine it like this. And now, it's interesting. So now I made a mistake in one step, that the amount of atoms which we located from the beginning, what we have, I'll show it to you, in here, were not correct. So this can happen. So we find out some additional atoms, and then we know, okay, they are fine, but it's not taken into account, so it's reason. You can see that it says the cell contents and the unit instructions list, meaning that that one doesn't agree. So we will now look carefully, because there are two things. I'm not sure if you noticed this. There are two possibilities now. Either my contents from the beginning was incorrect, or I have incorrect atoms in here. And now this requires a quiet. I'm not sure if even your boss realized this, that the computer program made a mistake. And this comes from the fact that the computer program doesn't know the atoms. The X-rays don't know the atoms, and they don't know how they are connected. So it's our business to see. And if you now remember, unfortunately I don't have it, but if you remember the 5-membered ring, in the 5-membered ring there is an sp2 carbon, which means that there's a double bond in there. In this carbon, this is also sp2. So if this hydrogen would be real, that would have a plus charge. And we would have to have an anion. So the computer was looking for it because it doesn't really know it, so it mathematically looks for the bond distances in here and there, and says, okay, yes, it seems to be that there's a hydrogen missing from this atom, and it places them. But we were lucky enough that the computer program told us now there is something wrong, so we were sure that this is okay, but now the computer says, no, this is not the same as that one. And then we realized, okay, chemically, this is impossible. So this, our understanding and knowledge about the chemistry what we have comes into a play. So we say to the computer program that you are incorrect. So we destroy this. We just go in there and I will do it like this. This doesn't work so well. Delete. So I remove it. Now I repeat a refinement. And now once more. Now everything's green. Now we have done. And adding one hydrogen makes our structure completely incorrect. It cannot be correct chemically. But this number doesn't change virtually at all. So all the numbers were green, everything is fine, except there is the remark. So you have to be really careful when you have the structure, when you analyze the structure, that is chemically reasonable. Because X-rays don't know. They don't know what atoms is and where is atom and so on. It only looks for the electron density. And we were not looking for the electron density in this area. It was just a computation what the computer was doing, the program. But that's that. So that's more or less, I think, everything what I want to show you today. Tomorrow, what we will do, we will go on continue from this, analyzing the structure. What can we do with the structure? We can look at the bond distances and angles and packings and all these kind of things and analyze that. And then finally, there will be a check if our structure is correct, is acceptable. And this is an additional thing we always have to do with the structures. And this process is called the check sieve. And that's why we have the ACTA here now. Where is it? ACTA here. That it writes, tomorrow I'll show you the zip file. And that's like a final file what we get from the structure solution. And there is additional service to check that everything is done correct. And nowadays when you are publishing a paper or you submit anything, you have to do the check. Then everybody can see that you didn't cheat anything, so that's corrected. But okay, that's that. So it took a little bit longer, but I hope that you get now an idea. So we will organize, discuss who wants to have these programs and so wants to play the game at home with your own computer, so we can easily do this. And maybe tomorrow we will log that when we have a break time or so. What is the time for this? Okay. Now everything is done for today. Tomorrow we continue. So thanks a lot.
So, do we have time for a question?
Yes, of course. Can you can ask? It's about we have 10 minutes.
Yeah. So,
But if you have any questions, so please ask.
anyone?
Yes.
Sir,
Yes.
one method for crystallization, that is vapor diffusion method.
Yes.
So in vapor diffusion method, we have like select a small chamber inside a big chamber,
Yes.
and in this small chamber we select a solvent where it is totally soluble,
Yes.
molecule, and in bigger chamber less soluble actually.
Yes.
Because it will create vapor pressure,
Yes.
but not interacting or less interacting with the
Yes.
molecule.
Yes. Yes. That's the idea.
Yeah. So what if we choose insoluble in bigger size chamber?
No, that should be. It should be so that it is insoluble through the bigger chamber, because it will go from the bigger chamber to the small one where the solvent or the molecule is. So it's not the other way around. So it should be so, because if your compound would be soluble in the solvent in the bigger chamber, it would not crystallize. So that's the idea, because we have to change the concentrate or solubility of our target on in the small chamber, not in the big one.
Yes.
So that's the idea of what happens. So it's like mixing two things, and then the idea is that sometimes you do this you have a solvent A and solvent B, and when you mix them, it changes color. So this is in principle the same thing. So we change the properties of that in the small one, and that will induce the crystallization. Okay?
Okay, thank you so much.
You're welcome.
Do remember that you guys have a test today, so please keep this session a bit short. You all will have time for asking Professor the question.
Yes, yes.
Good afternoon, sir.
Yeah.
Sir, I have a question that do radioactive elements undergo diffraction?
So, sorry, do what?
Do radioactive elements
Yes, of course. Yes, 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 sir. Any element will diffract. And the radioactive elements are normally the heavy, big ones. And they diffract extremely strong. So we have done work with uranium. It's not very radioactive, but they diffract in the same way as anything else. But of course, they are very dangerous to use because you can do this. I know it's been done, but then you have to have a protected environment because the crystal will also radiate. It will be radioactive. So it's exactly the same.
And so the last question is,
Yes.
you said up to minus 20 degrees Celsius, the,
Yes.
the chemical properties like the orientation and the lattice energy
Yes.
of a crystal remains intact.
Yes.
So if the temperature goes down more, like if it comes to minus 25 degrees Celsius,
Yes.
is there any deformation of the lattice? Or
No, no. So the point is, I didn't tell you, but normally we measure everything in minus 150. So in the instrument, we cool down the crystal. But when it forms, then there's very seldom there is a big change. There can be so-called phase transition, but normally that's not the case. So when you get the crystal, then normally that will be stable in that on that temperature. So in that sense, it doesn't matter. It just forms in minus 20, and if you can keep it in minus 20 and put it in the diffractometer, and then go even lower in the temperature, it doesn't change. But if you go higher, it will melt. So that's the idea. It's just when you get the crystal formation happen, that's only the point.
Thank you so much, sir.
Okay, thank you.